Welcome back to Puzzling Adventures, where we once again look at some programming puzzles and I walk you through my way of solving them. I am, to no one's surprise in particular, still Philip Blank, and today we will be looking at some problems on binarysearch.com. In case you don't know it yet, you might notice the site looks rather familiar to the popular lead code. It has a number of problems, all of which are categorized as either easy, medium, hard, or harder, and once we look at the interface for actually solving them, that too looks quite familiar. We have a description of what we are supposed to do on one side, and an editor to actually do it on the other. You can select among a number of languages, so unfortunately the site only supports 6 of them. My favorite one, C++, is still there, so I am happy, but your mileage might vary here. Once you have solved your problem, you can of course, as usual, click a submit button to get it tested against a number of test cases. If you did succeed, it will not only tell you that it did so, but it will give you a detailed comparison of how well you performed, both in terms of memory usage and runtime, compared to all the other submissions on the site, which is really useful for evaluating your solution. Another cool thing is this feature for sharing solutions, where you are encouraged to not only provide an explanation of what you did, but an intuition of why that might have been a good idea, and also an analysis of both its runtime and space complexity. That yields quite a lot of high-quality explanations on the site for pretty much all problems, which is quite educational. But the one feature that really sets this site apart from all the others is this ability to create a room. In this room, you can work either collaboratively or competitively with a number of other people. You can select what kind of problems you want to appear, so if they should just be of the easy category, medium, hard, or harder, and you can select who may get into the room. If you set it to public, everyone can participate and watch what you are doing. Otherwise, you can also just allow friends or people you explicitly invited. You can select how much time will be allocated for all the problems, and you can select whether or not it will be a contest. If it's a contest, of course, the first person to solve all the problems will be the winner. What really sets it apart from things like Clash of Code, where you only have that competitive aspect, is of course this collaborative one. Once you solve all the problems, you can actively see what others are typing and help them in any way you want. That really helps all of us to become better programmers and is a cool feature. None of that really matters for today though, because I have already selected the problem we are going to solve, and it is this one. As usual, it pays to first read what we are supposed to do, so I suggest we do so, and in case you want to think about it before hearing my thoughts, the best thing would be to pause the video now. See you soon. If you did pause to read the problem statement, welcome back. If you didn't, thank you for staying with me. Now, in the interest of full disclosure, I have to of course reveal that this is not the first time that I'm confronted with that kind of problem. It might be the first time I'm solving this particular version of it on this particular site, but Twosome is a rather popular and well-known problem, so of course I've encountered it before. For instance, it was used in last year's Advent of Code, and I've already written a detailed blog post explaining all of my solutions for Advent of Code, so you can already find some explanation in writing written by me on my blog, which I'll link in the description below. So what I can't do in this case is really provide you with my first thoughts on encountering it, because I really don't remember them. So what I do instead is give you an explanation of various, increasingly more sophisticated, more efficient ways to solve it. Before doing that, we should of course make sure that all of us are on the same page, and as such I read the problem statement and comment on it. So we are given a list of numbers, nums, and a number k, and we should return whether any two elements from the list add up to k. We may not use the same element twice, but they may be negative numbers. Then we are shown an example, input, output, and even an explanation of what the solution is and why it is the way it is. The input is the array of numbers 35, 8, 18, 3, and 22, and we are supposed to search for two elements in there that sum up to 11. The output we are supposed to give is true because if we add 8 and 3, that gives exactly 11, what we are supposed to check. If we had chosen any other number, so had we chosen 18 and 22 for instance, the sum would be 40 and therefore not 11. So if we removed any of the values, either 8 or 3, the output would of course have to be false, because now we could not find any two elements that sum to 11. Well, the simplest and least efficient reasonable way to do that is really compare every pair of elements. So iterate over all of nums, then for each entry in there, iterate over all of nums again, sum the two elements, see if it is 11. If it is so, return true. If we manage to iterate through all of it and not find two values that sum to 11, we have to return false. So let's quickly code that one up. We start with a simple for loop to iterate over all the elements. In there, for each of those elements, we have to iterate over all the other elements. So we need a second for loop inside that for loop. Now the two elements may not be equal, so we cannot use the same index for both. So the worst and easiest way to do that is just check if they are the same and then go to the next loop iteration. Otherwise, we have to check if they sum to the target. So we have to do if nums at position I plus nums at position j equals the value we want to search for, k, then we have to return true. And in case we manage to walk through all of them and not find one, we have to return false. Now, if we run that, we notice it works for this test case. We even given a second example, so we could run it on that one too before submitting it. And we see it works for that one too. And let's quickly check the third and fourth version to make sure that all the provided test cases guarantee we are doing the right thing here. Oh wow, there are a lot of test cases. Works for that one as well. And now we have the last one here. And for that one, it too works. So it's time to submit and see how we actually did here. Wait a moment, because that might take a while because our algorithm is rather inefficient, and here we see our problem. The time limit has been exceeded. We took too long to find numbers that sum. The test case is of course rather large and just an array of a lot of ones, and we are supposed to find whether k equals 3, so we have to compare all of those ones with all of those ones, and we figure out that it never equals 3. We would eventually come to a conclusion, but it takes a long time. So we should think about how we can improve. The first thing we can improve is get rid of this continue and this starting at the same index, because we are actually comparing each element twice currently. We are starting with element at position 0 and comparing it to all elements from 1 to n. Then we are looking at position 1 and comparing it to 0 again, and then to all the other elements. Then we are looking at position 2, compare it to 0 and 1 again, and then at all the other elements. So a different way to get all pairs and to really get all pairs just once is to start the second loop in here with one higher than the outer loop, because all the other ones were already checked exhaustively with all elements, so we don't have to check them again. That allows us to remove this continue, and our code should be a little faster. It shouldn't be a lot faster because, okay, before that we checked each pair twice because we checked it with the first one being I and the second being j and the other way around. But now we check it only once. So our runtime should be cut in half, but a factor of 2 isn't that much in so large quantities. So let's just submit it again and see whether we were good enough. And we notice we weren't. So at that point, we have to sit back and reconsider whether we really have to compare every element with every other one, or if there might be a better solution. To figure out how to further improve our runtime, we have to consider what we are currently doing and why we are doing it and why it is slow. So first of all, how fast is our solution? Currently, we are iterating over all elements, and for each element, we are iterating over all other elements. So n times we are doing something of the order of n. So n times n, which is n squared, quadratic. That is a lot. Why are we doing that? We are doing that to enumerate each pair of elements, to compare that to a certain value. And that is, of course, one way to look at both what we are doing and how we can solve it. But there are other ways to look at it. For instance, if we look at this first loop, we just select one element out of all of our array, and then what is it the other element actually does, the other loop actually does. It goes through all other elements until it finds one specific one with one specific property. We are searching for that other element that, when added to the first one, equals k. So with a bit of mathematics, we can figure out that we are searching for exactly the element with the value k minus the first value. So what our inner loop actually does is a search in the array. It doesn't just iterate and compare pairs, but it searches for one specific element. But it does it in the least efficient way possible by comparing each element. So the question is, can we search for an element faster than linearly, faster than by comparing each element? And in our current case, we cannot, because the array is just arbitrarily ordered. And if we have no idea about the structure of those values, how they are laid out in memory, we can't really know more than the one element we looked at. If, however, the array was sorted, we could do that. We could do it fast. We could actually do it in order log of n. Here we are again with an almost blank sheet of paper, which I'm going to ruin in a moment. And I've already prepared a perfectly sorted array on there. So each of those small squares is one slot in the array, starting from 0 here, 1 here, and so on. So this is array at index 0, this is array at index 1. And what you'll notice here is that each value is larger than the one that comes before it. So -2 is larger than 9, 1 is larger than -2, 5 is larger than 1, and so on. So this array is sorted in ascending order. Every element to the right is larger than all the elements that came before it. So this allows us to actually search rather quickly. Assume you want to search for the value of 12. What we did previously, when we did linearly, we said we compare 12 to -9, 12 to -2, 12 to 1, 12 to 5, 12 to 6, 12 to 9, 12 to 12, and then we'd have found our element after making 7 comparisons, which is rather a lot. If we had searched for 21, it would have been even worse, and we would have compared every element. But here we can abuse the structure to get rid of multiple elements in just one step. Assuming you compare 12 to exactly the middle element, which in this case is 6. Assuming we compare 12 to 6. We'll figure out that 12 is not only not 6, but 12 is bigger than 6, right? And luckily for us, that bigger-smaller relation is transitive. So if 12 is bigger than 6, then of course we also know that z is bigger than 5, and as such, 12 is also bigger than 5. We also know z is bigger than 1. We also know z is bigger than -2. And we can do all of that for all those elements. So just comparing with the 6 in the middle will yield that 12 is bigger than all the elements left to it and the 6. So what we can do now is actually strike out all of those elements. They aren't relevant. We know even without looking at them that they cannot be our 12. They are all smaller than 12. So we are left with just all those elements. And now we can once again look at the middle element here. Okay, we have unfortunately now an even number of elements, so what is the middle element isn't exactly clear. Let's, for this case, assume we round down, because then we can illustrate our point better, because we land on exactly the 12 after just having asked 2 questions. Is 12 bigger than 6? Yes, it is. Is 12 12? Yes, it is. Cool, that was rather quick. Let's run through it with a different example just to get a bit of a feel for what we are doing and how it works. So once again, let me write down that same array again. And please try to ignore my ugly handwriting. Even if you complain about it, I won't get better at it. So it's best to just try to follow along what I'm saying and ask in the comments if anything is unclear, and I try to elaborate with, I don't know, vector graphics or something like that. But for that, I believe it should be clear enough. So here we have the same array again, and now let's search for a different value. Let's move that up a little so it can be seen clearly. And now let's search for the one that was the worst case in the previous case, which is a 21. So let's search for 21. What questions do we ask? We again start in the middle. Ask, is 21 bigger or smaller than 6? 21 is indeed bigger than 6, which again allows us to strike out all of those elements, because all of them are smaller than 6. So if 21 is bigger than 6, then obviously 21 will also be smaller than those, bigger than this, so it's not smaller. Okay, so we are left with 9, 12, 17, 21, and again we are left with an even number of elements, so we have to round down or up. We have to do it consistently, always round up or down, but For now, I'll just round down again because it will be the worst case in this particular example. So we compare with a 12. So the question we're asking now is 21 bigger than 12? Yes, it is indeed. So we can throw away those two elements again because 9 is smaller than 12 and we know that without looking at it. So we are left with 17 and 21. Round down again, look at 17. Is 21 bigger than 17? Is 21 bigger than 17? Yes, it is. So we can throw away the 17 again, and now we look at the 21 and actually found it. So what did we have to do? We had to compare 4 times. We had to compare 21 to 6, 21 to 12, 21 to 17, and in the end, we had to compare 21 to 21 again. So here we took 4 tries, but 4 is still significantly smaller than the 9 we would have done had we done a linear search, right? So can we quantify how fast this works in general in the worst case? Turns out we can with just a tiny bit of mathematics and a bit of logic. So let's try that. In each step, we halve the array we have left. So if we start out with 10 elements, what we are left after one step will be exactly half of that, so 5 elements. In our case, we start with 9 elements, so let's do the example here. We start with 9 elements, and after the first step, the most we would have left is exactly 9/2. And let's take the worst case here and round up. Then we'd have left 5 elements after one comparison. Even if we hadn't found our element yet, we would have to do that again. So if we have not found our element, we would have to once again divide 5 by 2. Once again, we round up to get the worst case, so we'd be left with 3 elements. After 2 questions, we are left with 3 elements. If we still haven't found our element, the one we searched for, we have to once again divide by 2. Again, I round up to get the worst case, which would in this case be 2. So after having asked 3 questions and we still haven't found our element, there are 2 elements left we have to compare. So again, we divide by 2. And now all we have left is one single element. So that must either be the element we are searching for, or it will not be in the array. So at this point, no matter which element we are searching for, we know whether or not it is there or not. And if it is there, we even know where it is. And for 9 elements, all we had to do was ask 4 questions in the worst case. We could have already found our element here, here, or here. But in the worst case, we had to ask 4 questions, divide our array by half 4 times. So how often can we do that? To know how often we have to do that, we have to know how often can we divide our length, the 9, by 2. So the question we are asking when asking how often do I have to do that process to find my element in the worst case is actually just the question is how often can I do the following? N divided by 2. N divided the result of this divided by 2. Then we take the result of this and divide it by 2. And how often can I do that until I arrive at exactly 1 element? So formulating that a bit more more mathematical and more formalized, what we are asking is n divided by 2 to the power of x is 1, and we are searching for the value of x. We are searching for which value, how often can we divide n by 2, so we arrive at the value 1. Well, if we just pull that over here, what we end up with is n equals 2 to the power of x. And that is exactly the question, that is exactly what logarithm is defined to be. So the logarithm to the base of 2 of the value n equals exactly the x we are searching for. So our runtime is as such O of log of n, logarithmic. The runtime of our linear search we had before was O of n, linear. So how do those two compare? Let's have a look. O of n, or let's just say n compared to log of n. And let's just name a few numbers here. Let's say we start with n2, what is the log of 2? How often can we divide 2 by 2 to get 1? That is exactly 1. That is harmless. Let's double that up. Now we end up with 2. Let's double it up again. We end up with 3. Doubling it up again will give us 4 here. Doubling it again will give us 5. You get the idea. So if we just extend the table a little further, you will see that the left side grows dramatically, whilst the right side always grows by exactly 1. So even in an array of just 256 elements, we would only have to search 8. We would only have to do 8 comparisons. In an array of 512, we would have to do 9 comparisons. In an array of 1024, we'd have to do 10 comparisons. So within just 10 questions, we can find any number in a sorted array of 1024 elements. So that is significantly better than the linear search. Great, now that we are back and equipped with newly acquired knowledge, let's see how we can actually make use of that. To translate what we sort into our code, we have 2 problems here. The one problem is our numbers aren't sorted, so we would have to sort them. The second problem is that we might have to implement binary search, and doing that correctly is actually surprisingly tricky. Luckily for us, we don't have to do either, because the standard C++ library already provides us with functions to do so. It actually provides us with 3 different functions for binary search, but let's ignore that and talk about it later and think about sorting first. Now, all of that, binary searching and finding our value quickly, would do nothing for us if sorting itself were more expensive than what we are actually trying to do. Luckily for us, sorting isn't that expensive. If we are sorting arbitrary numbers and we know nothing about them and all we can do is comparison between single elements, then the best case we can get, the best sorting algorithm we can find for that, works in order of n times log n. I would love to go into detail about that and explain some sorting algorithms, but I fear that is out of scope for this particular video. But if anyone is interested, just send me a message and I'll see if I can elaborate on that a little further in a different video. But just note that sorting, if we call sort, that works in order of n times log n, which is faster than what we are doing here, and therefore it's worth it. So sorting in code is actually pretty trivial here. We just call sort, and then we pass the range of the things we sort, which in our case is from the beginning of nums to the end of nums. Rather straightforward. Alright, now the binary search. There are 3 functions in the standard C++ library for binary search. They are called binary search, surprising name here, or lower bound, or upper bound. They basically do the same thing, but they differ in what they return. Binary search, the first one here, just returns either true or false. It returns true if the searched for element is within our collection, and it returns false otherwise. Which might be exactly what we need here, as we aren't supposed to actually return the pair, just whether it exists. Lower bound returns the first element that is not lower than the target we are searching for. So if it is present, that will be the element we are searching for. If it is not present, it will be the element after the position where we would have to insert it into the collection, so it would be sorted. Upper bound returns the first value that is bigger than the value we are searching for. So all of those have different use cases, but in our case, all we need is binary search. We just need to know, is it there or is it not there? So with that, we don't need this loop, but we need to know what we are searching for. So let's call the variable target, and the target is the value of k minus the first value we are looking at, so minus the value of nums at position I. And then we have to search for it, which we do with binary search. Binary search, again, gets as its first parameter the beginning of the range, as its second parameter the end of the range, and then the value we are searching for. So we shouldn't start at the beginning here, actually, because then we might find the value nums I twice, and we aren't supposed to use the same element twice. So if we are searching for the value 6 in example 5 over here, if we just started and searched the whole array, we would suddenly get true here because it thinks 3 plus 3 is 6, so that's what we're searching for. But that is not what we want. We only want that if the element is actually a different element that adds to that. So if there were 3 in this example, were two values of 3 in this example. So we can't search the whole range, but we can do the same trick we did with the loops earlier and just search everything that comes after, knowing that the stuff before was already checked. So we can say we begin our search at nums begin plus I plus 1, and the collection goes till the end, and the value we're searching for is target. So of course that's just a search. We now have to return true if that returns true. So if this returns true, then we have to return true. And if we run through all of our elements, then we return false. Now, theoretically, we can analyze the runtime here and know this one is order of n times log n. Then this loop runs n times, and this step, the searching, is log n. So this whole loop taken together will do n times a search of log n. So this loop itself will run in order of n times log n. So the total runtime of our algorithm will be 2 times n log n, and constant factors can be ignored in algorithm analysis, so it's still order of n times log n. So let's ignore the comments, because code is clear enough, and if it was hard to read, it should be hard to write. No, I don't really mean that. Please don't follow that advice. And then let's run it on a few examples to see if it actually returns the right values. And apparently it does. On the first one, let's see with the second example. And if we are confident enough, we can submit and see if it now is fast enough to solve. And it's fast. It's fast enough that we actually succeed here and don't fail with the timer. But if you look at the details here, they say the code took 67 milliseconds and it was only faster than 4.70% in C++. So 95% of all submissions are still faster than this solution. So there must be a better way. Let's think about that better way. Today I'm really jumping a lot between pen and paper and my desktop, so if that is disorienting, I apologize. Please feel free to let me know in the comments below if you want more or less of that sort of thing. Now, I've prepared another array, again sorted in ascending order, to demonstrate how we could improve our runtime any further. Let's assume we are searching for 2 values that sum to the value 16. So, not as in the binary search, we have one value given and search for the other one, but really search for the 2 values. So don't do those 2 steps where we first look at -2, then search the rest of the array, then look at 1, search the rest of the array, and so on. Now, if we search for 16 and look at that quickly, we can do it manually and notice there are multiple solutions. We could use the 13 and the 3, and the 10 and the 6, and so on. But can we do that structurally in a way that avoids sorting, avoids searching through all of the array for every element? Let's start with a simple hint. Let's say we look at the sum of those 2 values at the extremes. So the smallest value plus the biggest value. What will that sum be? That sum will be 13 plus -2, which is exactly 11. So this sum is smaller than the value we are looking for. 11 is smaller than 16. So whatever we do now, how we change which values we look at, we have to increase the sum. Can we increase that sum by looking at any other value of those, by ignoring the 13 and looking at any of those other values and keep the -2? We cannot, because every value here is smaller than 13. So if we take the -2 and add any of those other values to it, the sum will decrease. It will be smaller than 11. So 10 plus -2 will be 8. 7 plus -2 will be 5. So we can exclude that the 2 will ever have to be summed up with any of those values. And any of those values ends the 13, so we can exclude the -2 completely. We know -2 cannot be in the sum we return, because -2 plus the largest value is already too small, and all other values are smaller than that. So we can exclude the -2 and say we now look at 1. So this one is completely ignorable. What we get now is 13 plus 1, which is 14 and which is still smaller than the value we are looking for. So we have exactly the same situation again, this time with 1. We have every other value here except the 13 is smaller than 13. So 1 plus every value here will always be smaller than 1 plus a 13. And since 1 plus a 13 is already smaller than the sum we search for, we again know that the 1 cannot possibly be part of our sum. As such, we can now look at the 3. And now we look at 3 plus 13, which is exactly 16, which is what we want to have here. So that's basically the algorithm, but let's walk through it once again and maybe get a better intuition of why it works and how it works by also moving the second pointer here. So let me quickly repeat myself and write down that same array again. I'm sorry, I forgot to do that in preparation. And now that I've actually managed to say some of my words correctly, I don't want to restart the recording if I don't absolutely have to. So here we are again with that exact same array as before. And let's this time search for another value that might yield more interesting results. Let's assume we are searching for two values that sum up to 10. So we are searching for A and B so that the sum equals 10. In this array, that would be 4 and 6, or 3 and 7, for instance. But let's not get ahead of ourselves and actually do the algorithm step by step again. We start with -2 and 13. Their sum, 13, plus -2, surprisingly still equals 11. It hasn't changed between our iterations, and 11 is bigger than 10. Now, set as a first in our iterations. When we did it earlier, we only ever had numbers that were smaller than the value we were searching for. But now we have a number that is bigger than the value we are searching for. So what we have to do now is get rid of our 13. And that is obvious because every other value we could use 13 with would yield a larger sum than the one we have. So if we used 13 with 1, the sum would be 14, which is larger than 11. If we used it with 3, it would be 16, which is larger than 11, and so on. So whichever value in here we would use 13 with, it would be larger than if we had used -2 with it, and that would be too large. So the 13 can be crossed out, and we look at the 10 now. Now we have the sum of -2 plus 10, which is 8, and now 8 is smaller than 10, is smaller than the one we are searching for, so we are back to the same situation we had earlier. We cannot use the -2 because no matter what we would use the -2 with, it would get even smaller. So -2 can be crossed out, and we have to look at the 1. Now we have 1 plus 10, which yields 11 again. So now our sum is too big. So again, we cannot use the 10 because no matter which number we use the 10 with, it would get larger. So the 10 can be crossed out, and we look at the 7. Now we look at 1 plus 7, which equals 8, again, too small. And if it's too small, we again have to move our small pointer because the 1 summed with any of the other values in between would be even smaller. So we cannot look at the 1, we have to look at the 3. And if we look at the 3 and the 7, yay, we have actually found what we were looking for. So what did we do here, and how fast is it? We started with the two values on the extreme, in the beginning and end. And in each step, we crossed out one of them. We excluded one of them because we know that the sum can only increase or decrease based on keeping it and using any other different value. So in each step, we can exclude one of them and slowly narrow in on exactly the values we are searching for. That always works because in no step did we exclude something we didn't know we could exclude because we always knew that value which we exclude cannot yield the correct sum. And in each step, we exclude one value. So we will definitely terminate after n steps because there are only n values to eliminate. In each step, we can eliminate one value. And since there's a finite amount of values in our array, of course, all of them will be eliminated eventually. So the runtime of all of that is order of n. Each step, we include one, we exclude one, and we can at most exclude n. So we have at most n steps. Compared to the runtime of our previous algorithm, that is better. The previous algorithm used n log n time because for each value, it did a search in the other ones. Here, for each value, we just do one comparison with the sum and then exclude one value. So we do n compared to n times log n, which is faster. For the total of our runtime, that doesn't do much again, because sorting still takes n log n, and that dominates the runtime. But in practice, it should be better, so let's try that. Great, so let's once again delete almost everything we did and do something else instead. So the one part we can keep here is sorting, and also the return false, because we still need to work on a sorted array, otherwise all of our assumptions about what we can exclude wouldn't work. So we can remove all of that with a binary search, but keep the sorting and keep the return false in the case that we didn't succeed. So we do need two indices though. We need one for the beginning and one for the end. So let's do that. The first starts at 0, obviously, and the second, the end, starts at the last valid index, which is the size -1. We try to find our element until start is bigger or equal to end, so until we don't have two pointers anymore, but they overran each other, or we have found our value. So we do a loop that works while start is smaller than end. Now, in there, we have to compute the sum of start and end of those two values, which means we compute our current sum, let's save it as sum, nums at position start plus nums at position end. So far so good, and now we have to compare that to the sum we are searching for. If the sum is equal to k, we return true. That's the easiest part. If the sum is smaller than k, what do we have to do? If the sum is smaller than k, we have to update one of our pointers, and that means we have to increase our sum, so we have to update the smaller of the pointers, and since we have sorted our array in increasing order, start is a smaller one, so all we need to do here is plus start. And if the sum is bigger than k, we have to decrease our sum, so we have to decrease the end pointer, move the right pointer one to the left. And I believe that's it. Let's try it with some of the test cases first. It works with the first one. Let's just randomly select the fifth again. Try it with that. And it works as well. So let's submit and see if we did any better. Oh, runtime error. So our code is wrong, or at least our code has an error, which is somehow for an empty array we crashed, we had a seg fault. Of course, because num.size would be 0, and then the end pointer would somehow be a really large number, because what size returns is size t, which is an unsigned type, and we subtracted 1 from 0 there, so we got a negative overflow, ended up with the largest possible positive number, and that is of course outside of the range of the array. So the simple fix here is to just return false if the array is empty, because that is always true. So if the array is empty, we always return false. So let's run it on this specific test case to see if it fixes that, and then run it on submit it again and see if there's anything else we missed. And no, we didn't miss anything else, and we got significantly faster. If I remember correctly, our time before was something around the 60 milliseconds, so we again improved by a factor of 2, and are now faster than 58.24% in C++. That is great, but it's still not perfect, is it? Because 40% of all submissions are still faster. So what can we do here? If you have watched and remember my last video, you might remember some small quip on the side which I made when I said that whenever complexity escapes us, we computer scientists tend to just throw a hash map at the problem. And in fact, in this problem, we can actually do the same thing. Earlier, when we did the iterate over the values and then search in all the values we haven't looked at yet solution, the ones that worked in order of n log n, what we did was assume, okay, we don't want to look at things twice, so let's just look at all the stuff we haven't seen yet to find the value. In this case, we can do the opposite thing. We could say, if we look at the first value, okay, ignore it can't possibly be a sum of its own. So let's save that and remember it. Remember that we have seen that value. Then look at the second value and think, is any of the values we have seen previously summed with this value equal to the sum we're searching for? So just look at, see if the value that is missing has been seen before. If it has, return true. If it hasn't, insert that value into our hash set, remember it, remember that we have seen that value, look at the third value, compute which value we would need to sum to the target, look into the hash map if it was there as well. So assuming lookup in our hash map, or hash set in this case, actually worked in order of 1, so in constant time, that would yield a linear time algorithm, because for each element we would just look up in the hash map, if it isn't there, insert into the hash map, and continue with the next element. So we would only look at each element once, or twice because we have the lookup thing, but just linear, no log n factor, nothing else like that, just O of n. So assuming our lookup into the hash map is actually order of 1 or close to it, that should be faster. So let's try to implement that now. Again, we delete everything we had. We don't even need the sorting now anymore, because the order doesn't matter if we just look at everything we have looked at before. What we need is a hash set to remember what we have already seen. So that is an unordered set, saving integers, and what it represents is what we have seen. And then we have to loop over all of our values. To do that, I now use a range 4, because earlier we had needs that index, but now the index is totally irrelevant, so why go through the additional hoops of counting that if all I want is every element in the collection nums? That's what the range 4 gives us. So the first thing we have to do is compute the target, as we did when we did the binary search. Compute which value is missing for this value and the other one to sum to k. So let's call it target again and say it's k minus v, exactly as we had earlier. And now the lookup is no longer binary search, but simply if scene.count at position of our target is bigger than 0. So if the hash set actually contains the target. If we had C++ 20 here, we could use contains, which would be more expressive because it can either contain 1 or 0 of them, never more, so count is rather confusing. But we don't have it here on the side, so that is all we have. So if the count is bigger than 0, so if we have that value in our hash map, then one of the values we looked at previously was exactly the value we have to sum the current one with to get the value k, so we have found something. So we return true. If we've run through all of our numbers and haven't found something, we return false. That's exactly the same thing as we did before. Now, that is linear, as you can see, because here we run through our collection once, and in each step, assuming the lookup into the hash map is constant time, we only do a constant amount of work. So let's run it with a few examples to see if it yields the correct results. Oh, it yields a wrong result here. What have I done? Ah, of course. I forgot to actually insert the value into the target, and if I don't do that, my hash map will always be empty and never find anything. So after we have looked up, we have to, of course, insert the value into our hash map. So the next lookup will consider that new value we just walked across. So run the code again. Cool, it's accepted here. Let's do example 5 again, because for some reason 5 is a number I look at a lot today. And here we go. Seems to work. Let's click on submit and see if it also works for the real test cases. And it seems to work, and it seems to be faster. It's not that much faster, as you can see, because we had 33 milliseconds and now we have 30, so a little faster, but we jumped up to be better than 86.01% of all submissions in C++, so there's only 14% of submissions that are faster than we are. But that's 40% too much, isn't it? So let's try to figure out what we can do to improve it further. I can see two possible approaches to improve our situation here. One of them involves perfect hashing, or rather the fact that our hashing currently is everything but perfect. And the other one involves reducing the amount of unnecessary allocations. Currently, our unordered set doesn't know how many values it will contain, even though we already know that in the beginning. We know it can never contain more values than we have in nums, so we could just pre-allocate that much and avoid it having to allocate again and again whenever it runs out of space. That could help our situation tremendously. The other thing is perfect hashing. the unordered set is generic. It doesn't know anything about the distribution of our values, so it cannot really provide perfect hashing. Even so, in theory, we could do so here. We know what values appear. We can iterate over nums and figure out what's the smallest value, what's the largest value, and that is the amount of values we could at most look up in there. And then we could pre-allocate exactly that many slots and just have one indexing operation inside that giant array. That does of course have some rather glaring problems. One is the huge memory footprint. The memory usage would now no longer depend on the number of values in nums, but on the exact values in nums. And as those are 32-bit integers, that could go to something like 2 to the power of 31 minus 1 or something, which is really, really large. And since we might have negatives as well, we are getting closer to 2 to the power of 32 bits required in our map. That makes me think that even if I implement that solution, it will probably run terribly in practice. But in theory, it could be better depending on the value distribution. And I think it's quite interesting from a theoretical standpoint, so I think I should quickly implement that, even though the chances of success here are rather low. So, first of all, to do our indexing into a giant array, we have to know how many indices there are and what's the lowest index we will ever use. So, we have to iterate over our nums and figure out what the smallest element is and what the largest element is. And then we know the range of values we will ever look up in that map. That range of values is from the minimum we will look up to the maximum we will look up. And that minimum is the minimum value we can get for target, which is k minus the maximum value in the array, or the minimum value in the array if that is smaller, and the maximum vice versa. So let's quickly do that. First, we figure out the minimum and maximum in the array. We could do that manually, but the C++ standard library already provides a function to do that. So let's use that. This will now return iterators to the smallest element in the array and the largest element in the array. So to figure out the lowest value we will ever look up, we have to do what I just explained. That is, it is either the minimum value in the array or k minus the maximum value in the array, whichever is smaller. To figure out the largest value we will ever look up, we will do the maximum of either the maximum value in the array or k minus the minimum value in the array, whichever is larger. That allows us to create a simple vector of bool, which is big enough by saying we take the highest value minus the lowest value, and since we start indexing by 0, we'll add 1, just to be certain. Now, if I add nothing here, it will just default initialize all the values, which in case of bool is false and exactly what we want, but I prefer to be explicit here and say that, spell it out. Then we have to change all of our accesses to say we no longer use count, but we just index into it at target, but we subtract the lowest index we ever look up, so we start at 0 instead of something like -2 or 5, just so that we normalize that and start at 0. Then inserting the value is similarly trivial. We just set the value to true. Now we have one more problem. Minimum and maximum do not exist if the array is empty. And then we'd have end iterators there and try to dereference that, which would be undefined behavior again. So if the array is empty, we just return false. Let's run that on one of the simple test cases first. And we get a compilation error because apparently I wrote seam instead of seen. Don't do that. Let's run it again. And it's accepted. Let's submit it and see how it did. And it did succeed, but the performance looks fucking atrocious. We have 365 milliseconds, 1 millisecond for every day in the year, and we are only faster than 0.49% of the submissions in C++. So quite horrendous, even though in theory it could be better. But we are doing two things here that might be rather costly. One thing is initializing that vector. Of course, every value in there has to be set to 0, so that alone will be order of the difference between lowest and highest, which could be significantly larger than the number of values in our nums. Also significantly larger than squared of that and so on. So that alone could be expensive. The next thing we are doing is no longer jumping around in small parts of memory because the map is small, but since our map is huge, we will jump into very different parts of memory to look up if something is present or not. And that could potentially ruin what's in our cache lines and be rather inefficient. So it was a good idea in theory, but in practice it just doesn't pan out always. It was worth a try. So let's get back and try the second version, as suggested earlier. And here we are again at the unordered set version. Let's quickly submit it to check that I haven't forgotten anything. Okay. And all we have to do to reduce the allocations is add the following line. We reserve enough space in our hash map for every value in nums. We could quickly run that on one of the tests. It shouldn't change anything about the functionality of the code, just about the performance. So now we can submit it. And it turns out, yay, we basically beat almost everything. 26 milliseconds, and we are faster than 99.21% in C++, and I'd say that's an acceptable margin of error for us. So I think we can be satisfied with that solution. To conclude our little journey here, I suggest we go through a few of the variations of this problem and solve those quickly, and then extend it to a little more than just two numbers. The first variation I found on the side is this one, which basically just gives us the list already sorted. And it demands that we do it in order of one space, so in constant space, which means we cannot use a hash map here. But the solution we can use, since the list is already sorted, is just the two-pointer one where we walk inwards. So we can basically copy that very same solution in here and it should just work. So I'm not a big fan of copying here, so let's just implement it from scratch again. So if the number is empty, we return false because then it cannot be satisfied. We could even go farther. No, let's not do that. Then let's say our start and end index. Start index is again 0, end index is again nums.size -1. And then whilst start is smaller than end, we again compute our sum, which is nums at position of start plus nums at position of end. And if the sum is equal to k, we return true. If the sum is smaller than k, we increment our start pointer. If the sum is bigger than k, we decrement our end pointer. And if we never return true, we of course return false. And fix our formatting to look a little bit better. Click on run. And click on submit because we are rather confident that we did it correctly, and we actually did it in probably the best possible way, 8 milliseconds faster than 96%. So that was rather easy. Let's look at a different one. Alright, here we are tasked not with finding two numbers that sum exactly to k, but to some value larger than that, but the smallest one of those. So we want to find the smallest value, the smallest sum that is still larger than k. For that, we cannot really use the hash map solution or the inward walk as easily. I'm not sure about the inward walks, that might work with some adjustments, but the hash map solution cannot work. But what definitely can work here is just doing the binary search thing and using upper bound to find the next larger value. So let's just do that quickly. We again sort our values. We remember our currently best sum, which means we need the slowest value we could start with. That will definitely be larger than everything we can find. And for that we just use numeric limits int max, so the largest possible integer. As we can assume that a solution exists, that will always be fine because it cannot possibly be larger than that. but it can be smaller. Then we do that whole walking over the indices again. And then we need to find the value that is larger than the one we are actually looking for if it was a target. So we construct our search target as a variable. And that search target is the target minus the value we are currently looking at. And then we try to find it. Notice how we use upper bound now, which gives us the value that is the first value that is larger than the one we are looking for, which is exactly what we are looking for right now. Again, starting at plus I plus 1 to not search for values repeatedly and not get duplicates. And we found it if whatever was returned is not the end iterator, but something else. If we have found that, we need to set the minimum to the minimum of what we had previously, and this new sum, which is nums at I plus the dereferenced iterator. I don't think we need anything more, so we can save on those. And in the end, we just return that result. Run it on the example. Looks good. Submit it. Looks good, so apparently we could have done better in speeds here. That's maybe something to think about. And here we have the next level in difficulty, not summing 2 numbers, but finding 3 numbers that sum to a certain value. We could here, of course, also go through all the different complexities and try to first do it in order of n cube, because we could do 3 for loops inside each other, nested, or we could do this, for loops and with sorted values, do the binary search thing, or we can just do one for loop and in there do the inward walk for the third value. I think that would probably be the most interesting one for now, so I'll implement that. We first of all sort our values. Then we iterate over all of our values. And then in here we have to do our inward walk, meaning we do the same thing with having a start index, which is now set to I, and an end index, which is of course set to nums.size minus 1 again. Then we can do while start is smaller than end. If we of course first have to compute our sum again. And this sum now is of course nums at position of I, and that tells me that the start here has to be I plus 1. And what we are basically doing in here is we are searching for the missing sum, so we have to compute what's missing at that point. And let's call that missing and set it to k minus nums at position I. Then we compute the sum here, which is nums at position start plus nums at position end. And then we have to compare it with missing, not with the k we are looking for up there. So if sum equals missing, we can return true. If, on the other hand, sum is smaller than missing, we have to increment the start pointer. And if sum is bigger than missing, we have to decrement the end pointer. If we run through all of that and never find a value, we can safely return false. Now, again, we have a bit of a problem with our indices that nums.size minus 1 would be some huge number if nums.size would be empty. So again, we special case that. We can run that on a test case. and see that we are doing something wrong because I'm not capable of typing in start anymore. The night has been far too long. But if I fix that, it runs with that, and I'll quickly click that bit again. And apparently it runs pretty fast, 84.44%. We can do a quick runtime analysis of this just for fun and see that, okay, sorting takes n log n time. Then we iterate over all values, and in there we iterate over all values with this inward walk thing. So that part is n squared. So n times log n is smaller than n squared, so n squared dominates. So the complete runtime of our algorithm is n squared. It's actually a rather interesting problem because we do not know if it is possible to get subcubic here. If you do figure out an algorithm that works in better than n squared time, please let me know so that I can take credit for it. Here we have yet another problem that is actually just sum in disguise. We are given a number of numbers as an array, and we are tasked with the problem of figuring out whether or not it contains any Pythagorean triplets. A Pythagorean triplet is just a set of three numbers, a, b, and c, that satisfies the equation a squared plus b squared equals c squared. Now, I claim that is basically just sum because finding two numbers that sum to a third number is exactly the inner part of our loop, and doing that for every third number is exactly what we did for our sum solution. We worked through our numbers and then computed which target we are looking for, and in this case it would just be exactly that number, and then we do our inward walk again. We can't exactly do that here because we aren't working with the numbers directly, but we are working with the squares of those numbers. So there are two possible solutions. The first and probably easiest would be to just replace every number in nums with its square, then sort, then do the normal sum stuff. The alternative would be to sort by the value of the squares and then do the sum modified with actually computing the squares as well. I'll do the latter one because it shows more stuff I haven't shown yet. So let's begin with sorting the array. We again pass the range, which is from the beginning of nums to the end of nums. And if we want to sort by something else than just the normal small operation, we have to pass in a comparator, so a function that tells us which elements appear before the other ones. In this case, we should probably look at the largest one first, because in a Pythagorean triplet, c is always the largest number. So, or the number with the largest absolute value. So we pass two parameters, which are the left-hand side of the comparison and the right-hand side of the comparison. And since we want the larger values to appear first, we should return true if a number is larger than the other one. So we return LHS squared bigger the right-hand side squared. Okay, after that, the largest squares are in the front, the smallest are in the back, and we can just do the same thing as we did with sum by starting at index 0, of course, iterating to the very end of the array, computing which target number we are looking for, and that target number will always be just this c, the number we are currently looking at first, and then we can do the inward walk to find two numbers that sum to this value. So we compute our target, or we save our target in a different value to make our code more expressive. And then we again need two indices, one for the start, which starts at one higher than the last one, and one for the end, which of course starts at the end of the array. Then we again wise that start value is smaller than the end value. Oh, by the way, the target is not nums, the target is num squared. Okay, whilst we are smaller than that, then we compute the sum. And that sum, of course, is now num start squared plus nums end squared as well, because we aren't working with exactly the numbers, we are working with their squares. And now we do the same thing as usual. If our current sum is smaller than our target value, then we have to increase the lower one of them, so we'd have to increase start. But wait, that's not quite right. In this case, since we sorted from big to small instead of small to big, so in descending order, not ascending order, we actually have to decrease end we are smaller because we want to get larger, and the larger ones are on the left-hand side, not the right-hand side. So we'd have to do this. If the sum is already bigger than target, we have to decrease our sum, and we do that by increasing our start. And of course, if the sum is exactly equal to the target, we can return true because we have found one value. Okay, and if we haven't managed to do that, we return false, as it's not possible. Let's run that on a small test case. Seems to be accepted. Let's submit it. And here we go. We are pretty fast. And again, just 3 sum in disguise. Unfortunately, this video is already rather long as it is, and I do desperately need to get some sleep. So I cannot really go into all the interesting ways we can expand on that problem. One way would be to just increase the number of values we sum. Do not do 3 sum, but 4 sum, 5 sum, 6 sum, and so on. All of that offers some rather interesting challenges, and there's some fascinating distinctions between how you can handle the odd cases, so when you sum 3 numbers, 5 numbers, 7 numbers, or so, compared to how you handle the even cases when you sum 2, 4, 6, and so on. And that is really quite fascinating. A good friend recently linked me a post on Stack Exchange where some of that was explained and there were runtime bounds computed for arbitrary values of k. That is really fascinating, and I do wish to explore it further, but I really don't want to abuse your attention for much longer than I already have. And as stated, I do desperately need sleep, so I'll call it quits here, and thank you for your attention, and that's all I've got for you today. See you next time. Thank you very much for watching. From this point onward, I'll just do the usual YouTube begging, so if you're bored by that sort of thing, feel free to end the video now. If you don't, however, and you enjoyed it, or maybe even derived something of value from it, please know that a single like can really make my day. What's even better is all suggestions for how I can improve my content or myself. So I'm eagerly looking forward to all your constructive criticism, your destructive criticism, and your threats of murder in the comments below. See you next time!